to begin with this section, we're doing things numerically. There are some functions that you can't integrate with algebraic techniques. So in that case, you have to have numerical approximations of an integral, of a definite integral. So we're going to look at that a little bit. The first thing I'm going to show you is a real simple concept, is if you're doing something numerically, you're approximating the exact value of the integral, okay, with a definite integral. So you have some sort of an error in the computation. So we're going to look at two different concepts here. First of all, the absolute error. All that is it's doing this, okay? Basically, one thing that you might want to write down is C is the approximate answer to the integral, okay? So you're doing an integral, and that's the approximation, okay, using some different techniques we're going to learn. And then X is the exact answer, the exact solution to the integral, like that. You might write that down, because all you're doing is you're comparing the exact answer when you can find it to the approximate, like that, and then you'll have some sort of an error. The idea when you do numerical integration is to try to minimize those errors as we can. And then when you're doing the relative error, you're looking more at a percentage. So what you're doing on that is you're just looking at, you're comparing this to the exact. Okay, so you'll end up getting what percent error that is. And the reason that we have absolute value, it doesn't really matter which order you subtract the two things in. Our error is going to be a positive answer. So error is always positive. Okay, so that's the reason that we're doing that. Okay. Okay, so I'm going to show you a couple of real simple things to begin with on here. So you may have learned at some point in time that a lot of times people have used the fraction 22 over 7 to approximate pi. Okay, so what I want to do on this is I want to compute both the absolute error and the relative error. We're going to use our calculator to do this. I wouldn't expect you to do any of this stuff that I'm doing right now any other way except use your calculator, okay? So like on a future exam, the calculator part, there's a lot of good calculator stuff in this section, okay? That's a lot of where I draw the calculator part of the test is from this section. Okay, so what we're going to do on the absolute error is we're going to get our calculator out, and we're going to do just kind of something simple. What we're going to do is we do C minus X. So again, when we do that, C is going to be the approximate answer, 22 over 7. Oops. And then pi, we're just going to use the pi key on our calculator because pi is an irrational number. The decimals go on forever. The further decimals go out, the better your accuracy is. So we're just going to do that, and we're going to approximate that on our calculator. Just if you want to get your calculator out, you can do this. So I just put this in one step like this. I do the 22 over 7, and then I subtract. I'm going to go ahead and use my pi key. I don't want to use 3.14. I want to just let the calculator use as many decimals as I can on that, okay? Then I'll just write whatever comes out on the calculator. So that's 0.0012644893. So you're pretty close, and really what happens on this, if you look at 22 over 7, if you look at that and if you compare that to pi, the accuracy is to 2 decimals. Okay, so you got 3.142, but 3.141 is the precise third decimal. So notice that when you have that 0.00, that means you're accurate to 2 decimal places. Okay, then it starts running into some error. So that's all an absolute error, an error is. Okay, next thing we're going to do is we're going to do the relative error. And this is where we get a percentage. Okay, so what we do on this is we just do the C minus X that we've already calculated, and then you compare that to the exact value. Okay, so you're always comparing it to whatever the exact value is. Okay, so what we'll do with this one is we're going to take the 0.0012644,893, and then I'm going to divide it by the pi, and then we're going to use a percentage on that. So what I'm going to do is just type it in like this, 0.00 12644 893, and then I'll divide by pi. I don't have to worry about the absolute value because pi is already a positive number. And you'll typically get these things in scientific notation. So we got 4.024 994452, and when you see the E -4, that just means that's scientific notation. So that's what that is, okay? So what that means is if you're going to look at this in scientific notation, this is really saying this. This is really saying move the decimal to the left 4, so you would have like 0.0004, like that, then you'd have a bunch of decimals like that. Now, if I convert this to a percentage on that, then what's going to happen on this is, and I'm going to take that out just a couple more like that, that would be what your relative error right there is then. And from that point, did I put that right on my calculator? Yeah, I think I did. Yeah, I got to multiply by 100 or just move the decimal over 2. I was just kind of thinking maybe I had something off a little bit on. There we go. That's it. So what I'm going to have on that is that's going to be about 0.04% would be about what that error is then. I just was looking at my notes that I posted, and I must have put something wrong in my calculator on that because I had that. No, I'm okay. I'm looking at the wrong thing. Okay, sorry. All right, so that's about a 0.04% error. That's what that is, okay? Okay, so there's nothing to that. That should be very, very straightforward and simple. When you're doing absolute error, you just subtract the two. And then when you're doing relative error, you compare that to whatever the exact value is. That's it, okay? All right, everybody following along okay? Okay, that's easy. Some of the easiest stuff we do all semester is in this section. Okay, so I want to go ahead and do the E now. So on this one, we're going to do let's do one more of these, then we'll start looking a little bit at the numerical methods of integration. So the absolute error, what we do again is we do C minus X, where C is whatever the approximation is. So in this case, I'm going to use 2.718. That would be like just 3 decimals for the exponential E. And then your calculator should have an E key on it. So you want to use that E key, okay, so that we get greater accuracy. So I'm just going to go 2.718. Then your E key is right above the division symbol on most of these calculators. So if you go minus and then second division symbol, you'll find that generally there on the TI. Then subtract this, okay? And see what you got to do on this. You got to do the absolute value. So since you're doing the absolute value, you have absolute value of 2.81828459, and then that's in scientific notation. And then you just want to have the positive answer. So I'll write that. I'm just going to write all the decimals that come out on the calculator. And you can write that in scientific notation. That's fine to do the absolute error. It's very common that it'll be in scientific notation, okay? All right, now what do you do with the relative error? It's just one simple thing. What do? You just take that number we got, and then you divide it by the exact answer, okay? So what I'm going to do on that is take this value, and I'm going to divide that by E. So I'm just going to do that on the calculator. I'm just going to keep me from retyping. I know I got a positive answer. I'm just going to go divide by and then press E like that. I'm going to get a negative answer, but it's got to be positive, so I'll just change that to this. And let's see, that's going to give approximately 1.03678896 times 10 to the negative 4. Then you can multiply that by 100 if you want to change that. Typically, we write that in a percent form. So that would be about 0.01% error is about what that would be then. Okay? So that's a pretty accurate approximation. So you're accurate within 0.01%. Okay, so that should be a piece of cake for everybody. You're going to use your calculator on that. You have to use your calculator on that. Okay? All right, any questions about that? Okay, and the idea of error will kind of We'll see that a little bit further in the class as we go through some other concepts. So you want to be able to do those two types of things. Okay, now we're going to go to what we call the midpoint rule. We're going to look at 3 ways to approximate integrals. What you did in Calc 1, and this really is something you should have done in Calc 1. You should have done Riemann sums with left endpoints, right endpoints, and midpoints. Now I'm going to do the midpoint. I'm just going to do one example of that. Then we're going to do a trapezoid rule, which you typically don't do in Calc 1. Then we're going to do Simpsons Rule, which also you don't typically do in Calc 1. Simpsons Rule is probably the most common, and the Trapezoid Rule is pretty common also. So what you'll do, a lot of you who are going to study engineering, you possibly will take a class called Numerical Analysis. And Numerical Analysis is where you look at things numerically. You look at integration numerically and differentiation numerically, and lots of things with approximations, with computer programming and stuff. Okay, so the midpoint formula, I'm just going to kind of talk through what this diagram is saying here and kind of go through some of the key things. So if you're going to approximate an area under a curve from A to B, so we would be on this problem just kind of looking at whatever our function is from A to B with some approximation. The idea is you're going to divide this into a certain number of rectangles, and you're going to use the midpoints to evaluate that. So the idea is going to kind of go like this. The midpoint rule, you don't have to memorize the midpoint rule, but what you're really doing is you're just finding the area of each triangle. So if you look at this triangle right here, we know that the area, did I say triangle? I think that's a rectangle. Okay, I'm having a bad day, it's so early. Okay, so this is a rectangle. So what's the rectangle? That's a base times height. Okay, like that. Okay, so the base is represented by what we call delta x. Okay, and that's just the change in x. Okay, so that's going to vary. The goal is to try to get delta x as small as possible. The smaller it gets, the more accurate your approximation gets. And then h is going to be the height, and that height is going to be whatever the function value is at that midpoint. So I'm just going to write this as the function value of whatever that first midpoint is right there. Okay, so delta x would kind of be like your dx in an integral, and then you're doing f of m1 like this. So what this midpoint rule is saying up here in this definition is we usually write this as m of n. So that means like if you had 8 rectangles, you would write that like m of 8. And what you're doing is you just do this over and over again. You do the function value of the first midpoint times delta x and so forth until you're done. Okay? If you were doing 8 rectangles, then you would stop when n is equal to 8. So that's what that idea is. Okay? Another thing that you're going to see me doing quite a bit is this formula right here for delta x. Delta x is b minus a over n. Now what is b and a? That's that's the integral. Those are the limits of integration, and what n is that would be the number of rectangles you're going to use. So what that does is that gives you how you chop up those rectangles like that. All right, so we'll kind of see that as we go. So you don't really have to memorize the formula. All you got to know is that an area of a rectangle is base times height. Base is delta x, and then the function value of the midpoint is what the height is. Does that make sense? Okay, I'll do a couple of one specific example that we'll kind of go through, and then we're going to do trapezoid rule. So that's all I want to say on this page mainly. Yes. Yes, okay. So remember what we did with Riemann sums is you typically either did a left endpoint, a right endpoint, or you even did a midpoint. It's the same concept. Yes, okay, good. It is. You did this in Calc 1, okay. What's going to be different is Simpsons Rule and the Trapezoid Rule. Okay, so let's do just one example of a midpoint. Let's see, did I give you this graph on your handout? I don't remember, okay. Yeah, that's kind of helpful if you have that. So what we're going to do on this one, we're going to do these things. We're going to get an approximation of this integral using 6 subintervals. And then we're going to get the exact value, because we would know how to integrate this. You could get the exact value. There's a pretty simple formula for integrating the sine of pi x. So the first thing we're going to do is we're going to do the midpoint rule. You want to start by doing delta x, and that's doing b minus a over n. And all that's going to do is that's going to tell you how to break up your subintervals, okay? So in your integral, b is going to be 1, and then a is going to be 0. So what you're going to do is you're going to do 1 minus 0. There are 6 subintervals, so it just means you're breaking that up into a sixth. You're integrating from 1 to 6. So if you divide it into 6 pieces, what's that going to do? It's going to go 1, 6, 2, 6, 3, 6, 4, 6, and so forth like that. So I'm going to go ahead and count these things out. I'm going to reduce the fractions kind of as I do this. So eventually we make it up to 6, 6, which is equal to 1. So what I'm going to do is let's go ahead and kind of divide this up like this. That's going to be a half there, and try to just subdivide this. That's going to be 1/6 there. 2/6 is 1/3. Then 4/6 is 2/3. Okay, then I got 5/6. And then 6/6 is 1, like that. So that's basically how we're breaking that up. So when you're doing that delta x, you're just dividing that integral into 6 regions like that. Okay? Everybody with me there? Okay. Okay? Now what we're going to do is we're going to do midpoints. So what we want to go ahead and do is we want to go ahead and calculate all of these midpoints. And you only have to do one of these, and then you can count out the rest. You don't have to do this over and over and over again. Sometimes I see students doing that. So let's find the midpoint between 0 and 1/6. Well, how do you find a midpoint? Well, you just subtract that interval, and you just find the average of those two numbers is what I'm going to do. So what you could do is you could just go 1/6 minus 0 over 2. Okay, so what that is that's 1/6 divided by 2. So that's 1/6 times a half, so that's 1/12. Okay, so the midpoint between 0 and 1/6 is going to be 1/12 like that. Okay, now you don't have to do that over and over again. You don't have to find the midpoint between 1/6 and 1/3. Just count it out. That's what I'm going to do. It's just go 1/12, 2/12. It's easier this way. And just keep counting it out until we get the last midpoint. Okay, like this. So I can just kind of go through and do like this. And then what I'll have from here is you'll kind of have a pattern here. So if you find this midpoint in here, you can continue to go through and kind of do this like this. Now this is not really counting this out. The next midpoint, what you're going to do is you're going to do the 1/6 right here. Then you're going to add on that 1/12 like that. Okay, and once I get the second one, you'll see a pattern. Then we can calculate this out. So I'm going to get a common denominator. Okay, like that. So that's going to be 2/12 plus 1/12. That's going to be 3/12 like that. Okay, so I'm just going to kind of start counting this out now. So I've got like 1/12. The next midpoint's 3/12. So what comes next? Odd numbers, right? 5/12, 7/12, and then 9/12, and eventually you get up to 11/12 like that. So once I find that first midpoint, I can really just count it out. It's just odds is what that is, okay? So I'm going to go ahead and write these out, but I'm going to reduce these. So 3/12 is a fourth. So that's what that midpoint is. And then this one is 5/12. And then this one is 7/12. 9/12 is 3/4. And then eventually we make it up to 11/12 like that. Okay? So it's arithmetic. As you're subdividing that up by a sixth, then you got to find the midpoints. Okay? Everybody following along what I'm doing on that? Okay. Okay? So that's usually what I do, is just find that first midpoint, and then I just add it, and then get the pattern, and just start kind of counting those things out. So the next thing that you want to do is you want to draw a picture of this. So what you do is remember your rectangle goes from the midpoint, okay? And you want to draw your rectangles around kind of like that. That's your first rectangle. Second one, go to the midpoint and go straight up to the curve, and then just draw a rectangle around like that. So that's rectangle number 2 and so forth. Okay, and then just kind of repeat the diagram using the midpoint like that. Okay, then the next one, go up and do that, and just kind of get a reasonable diagram so you can see what's going on. Okay, now one thing I want you to notice, and you learned this in Calc 1. So the thing about this is that's kind of nice about the midpoint formula is notice this rectangle right here, it kind of overestimates that, right? But it underestimates that. So it kind of balances out, not perfectly of course, but you kind of have an overestimation and an underestimation as you go. Everybody see what I'm talking about there? Okay, so all we need to do on this midpoint is just find the area of each of those rectangles and then just add it all together, okay? And this is a good problem for a calculator. Now I'm going to use fractions on this, and we are doing a sign. So this one I try to design so it goes to the unit circle mostly. So when we do our approximation, what we say is we say M6. Okay, that's the notation you want to learn. That just means we're doing midpoints using 6 subintervals like that. Okay, so it goes like this. Okay, what we do is we do basically this. We do delta x times f of the first midpoint. Now I'm going to write this out just kind of so because I want to get you comfortable with writing the formula out. The next thing we do is we do delta x times f of the second midpoint. Now you don't have to write all these out. You can kind of do this abbreviation. Eventually you get to times delta x, and you do the function value at the 6th midpoint like that. Okay, so that would be what we ultimately want to go through and do. Okay, so when we put this together, notice on here, what do you notice about that delta x? Just algebraically, couldn't you just factor the whole thing out? You might as well because it's simpler. Okay, so we're going to factor that out, and we're going to write this as delta x. Then we're going to go ahead and just start doing our function value. So if you go back to the function now, the function that we're integrating is sine of pi x. So I'm just going to take all of these midpoints, I'll kind of highlight these midpoints, and we're going to plug those in, and then we'll kind of see where we're at with this. Okay, so that's going to be, first one is going to be the sine of pi, and then that first midpoint is 1/12 like that. So we're going to have that. Okay. Then the second one, we're going to have sine of pi times, and that was a 1/4 is what that is. Okay, and then so forth. Then we go sine of pi times 5/12. And then the next one is the sine of pi times 7/12. And so forth. So let me erase some of this stuff that's getting in the way here. Let's take this out a little further here. So we got that. And then the next one we're going to have is the sine of pi times 3/4. And then the last one is going to be sine of pi times 11/12 like that. Okay? So that's how we're going to put that together. Now what we're going to do is we're going to get some of this stuff's going to come from the unit circle. So delta x, we found delta x to be 1/6. Okay, that's what we got kind of at the beginning of the problem, was we got that delta x. So we're going to have 1/6, and then we're going to do all of these things that we can look up on the unit circle. Some of these things I already did. I'm going to go through just a couple of these things. So what I'm going to do with this, and we could also just use our calculator on this, not all these things go to the unit circle. So this first one right here, let me see if I did this. Yeah, I think I'm just going to have you do this on the calculator. So I'm going to write one more step, just make it a little cleaner, and write it like this. And then we're going to get the calculator out. I'm going to kind of double check what I calculated. And some of these things go to the unit circle, some of them don't. So that's why I'm just doing the calculator. Okay, so let's see. Let's go ahead and let me get my calculator out. And what I'm going to do is I'm just going to do this. You want to be in radian mode. Then I'm just going to do all this in one kind of key step. I'm going to do what's in the brackets. So I'm just going to do this. Okay. So I'm going to go sine of pi over 12. Like that. And I'm going to go sine of pi over 4. And sine of 5 pi over 12. Wouldn't you rather just integrate this thing? Which is what we're going to do here in a minute. To me, this is sort of a pain. But there are times that you're going to see integrals that have to be done numerically. So that's the reason we spent a little bit of time going over this.
Care to see an example?
What's that?
An example of one that would have to be numerically done?
Oh, there's all kinds like that. There's all kinds of functions that you could come up with. I could give you all kinds of things. What if we had the tangent to the 25th power?
Okay.
Okay, something like that. You know, when we learn how to do integration, we kind of limit it to special things that can be integrated with certain techniques. God, I hope I'm putting this in right. Now, the one that we're going to do, this one does integrate. So, and part of the reason I'm doing that is because I want to show you the concept of the error. Okay, so I got that, if I did that right. Now I got to multiply everything by 1/6. Don't forget about the delta x, so I'm going to divide that by 6. Okay, so I get this. Okay, yeah, and that's what I have on my notes. So hallelujah, I got that right. Okay, so let's just write that down. That's approximately 0.64395055509. Okay, and I'm going to use all those decimals because we're going to get a approximation. Okay, now for your purposes as a student, I know a lot of you are going into engineering. You know, people don't do this much anymore. I mean, you get computers to do stuff, but when you're a student, you're learning concepts, right? If I don't teach you concepts, you wouldn't even know what the computer's doing. So that's part of the thing, is get these concepts down. So back in the old days, you had people had to crunch these out. Computer programs do this pretty easily for you now. So let's go ahead and let's do the integration now. And then we're going to do the absolute and relative error, okay? So actually the integral on this one's pretty easy to do. So we're just going to do the integral 0 to 1 of sine of pi x dx. Okay, do you guys know what the antiderivative of sine pi x is? 1 over pi, negative cosine pi x. Good. Okay, right. So there's a formula for that, and we've learned that before. You go, if you have a number in front of x, you say 1 over that, okay, which is pi, and then the integral of the cosine of the sine is the negative cosine, so you'd end up having cosine pi x, like that, and then you'd have a negative like that, and then you're going to integrate that from 0 to 1. Now we're going to get an exact answer on this one, so we can get this exact with pi and everything. Okay, so what you're going to have is negative 1 over pi. Then we're going to have cosine of pi times 1 minus cosine of pi times 0. Those are going to be two things that fall on the unit circle. So what you'll have is negative 1 over pi times cosine of pi minus cosine of 0. Okay, on the unit circle, for instance, at 0 you have the point 1, 0, and at pi you have the point negative 1, 0. So tell me what the cosine of pi is. Negative 1. How about the cosine of 0? 1. Okay, x value, right? Okay, trig stuff. So that's negative 1 over pi times negative 1 minus 1. So that looks like negative 1 over pi times negative 2. So it's 2 over pi. See, I'd rather just do integration. You would too, right? And the thing is, it's exact, okay? But the point is, you find a lot of times in engineering and sciences, you're doing a mathematical model and your integral is too hard. You won't even find an integral table that'll give you a formula, so you got to do things numerically. It's very common, okay? So what we have now is we've got the approximate answer and we have the exact answer. So what I'm going to finish up with is let's see how accurate we are. Partially, the other thing that we're kind of learning, you didn't do this in Calc 1, we're looking at the error in the calculation. So we're going to do these two things. So the absolute error is a real simple thing to compute. When you do the absolute error, the formula that was on the first page was C minus X. What is C? C is the approximate answer. So what we would do is we would take the 0.6439, 505509, and then subtract off the 2 over pi. And it's absolute value, it just means because that's a positive value, okay? So I'm going to take this number, and I'm going to subtract off, I'll use my pi key. Whoops, got to do this like, not like that. Got to go divide, and then that, and then that'll give probably a lot of times scientific notation, not in this case, so that's going to be about 0.00733077785. So that's how accurate you are. So you're basically accurate within a couple of decimal places. Okay, so that is your absolute error. Now let's do the relative error. What did you do on the relative error? What did I show you? You just divide that number by the exact. So when you do this relative error, the formula is C minus X. You take the absolute error and you divide it by the exact value. So if I just take this number right here and divide it, now what was our answer? Our exact answer was 2 over pi. So you need to be sure you have that in parentheses when you do that. Whoops, I keep doing the wrong thing. So I'm going to go divide by 2 over pi like that. I keep doing the wrong thing. There we go, finally. Okay, so if I do that, see, all you're doing is comparing the difference in those values. You're comparing that to the exact value, okay? So that's going to give, for a relative error, about 0.011515159. And then if you change that to a percent, you can move the decimal over 2 places, or you can multiply that by 100. So what you'd end up getting for your error is about 1.15%. So that would be how much of an error you have. That's pretty accurate, okay? And the thing about this is, numerically, what you would do to make it more accurate, what would you do with the number of rectangles? You just make them bigger and bigger. So, I mean, with computers, you can get really super accurate, I mean, in engineering, to the point where you want to be anyway. Okay, you don't have to have 1,000,000 decimals of accuracy with engineering problems typically. You got to have things approximate to some value. So if we did 100 rectangles, we'd probably have the kind of accuracy we would want anyway. Okay, so that's the idea. Okay, so that's midpoint, and that should look fairly familiar from Calc 1. Do you guys have any questions about that? Okay, right. Now, in this kind of problem, you got to have your calculator on. I'm not going to have you do this without a calculator. Okay, so let's go ahead, and the next thing I want to do is what we call the Trapezoid Rule, which is different. This is something that you don't typically learn anything about in calculus. And I think your TI, when it does these things numerically, I don't know for sure, but I think it's either going to be using the Trapezoid Rule or Simpsons Rule. It's one of the two. And the Trapezoid Rule kind of gives you a little bit different level of accuracy. So a couple of things that you have to know to understand what's going on the math on this is you got to understand, first of all, trapezoid's a 4-sided figure. 2 sides are parallel, the other 2 sides are not parallel. So you have one set of opposite sides that are parallel. And let's see if we remember the formula. You got to remember that. So what we have is we have 2 bases. Usually you call that base 1 and you call that base 2. And then you have a height. Okay, does anybody remember what the area of a trapezoid formula is from your background? 1/2 the height times sum of the bases. So write that down. That's important. So you have 1/2 times the height. times the sum of the bases. Okay, that's the trapezoid area formula. Okay, so I'm going to do sort of a trapezoid that way because that's the way you have to look at it in your function typically. So like here's just an example of a trapezoid. Let's do the area of this. So if you did this, you would do, the area would be 1/2 the height. The height is 6 centimeters. Okay, and all that height is it's just the distance between the bases. It doesn't have to be pointed up and down, it's just the distance between those two things. So we're going to have that height, and then we got to sum the bases. So it doesn't matter which way you do that, of course, so we just sum those up. Okay, so let's see, that would be 3 centimeters times 6 centimeters, so that would be 18 square centimeters like that. So in order to understand the trapezoid formula, you got to understand that formula for finding an area of a trapezoid, okay? And then from there, let's kind of, we'll begin to put this together, okay? So this diagram is showing the trapezoid formula, and there is a shortcut to the trapezoid formula, and I'll show you where that comes from in a little bit here. So basically what you're doing with this is, again, delta x is going to be, there's a couple things I want you to write down. Delta x is really the height of the trapezoid. Okay, so if you look at this function right here, what we're doing, this thing is not, I took this out of the book, it's a pretty good diagram. So what's going on with this is, like if you look at this right here, this is a trapezoid. So you've got delta x is the height. The height is the distance between the bases. Now the bases, aren't they just function values? Okay, like you would have whatever f of that number is would be that height right there. So what you're doing is you're doing this formula, you're doing half of the height times the sum of the two bases, like that, over and over again. Now if you look at the trapezoid, let me ask you this question. In comparison to the midpoint we just did, does that look more accurate or less accurate to you? What's more accurate, doesn't it? Because you've got that, you don't have that overestimated and underestimated. Depending on the curve, of course, and the curvature, that actually gives a pretty nice approximation. Okay, and then what we're going to learn a little bit later is Simpsons Rule, which just looks at a parabola there. And once you have a parabola, you start getting super accurate. Okay, so that's kind of the idea, is we're going to use trapezoids because it increases the accuracy a little bit. Okay, now the formula has some shortcuts in it, which I'm going to go through and show you how that comes from in a minute, but I'm not going to do that yet. The best way to show that is just with an example. So what you're doing is you're summing all these trapezoids up. So again, delta x on these is always b minus a over n. Okay, so like if you have an integral from a to b, those are the limits of integration. Okay, and then n is the number of trapezoids that you're going to use. Okay, now this trapezoid formula is a shortcut. There's some factoring that goes on in it and some things that can kind of be simplified. So the formula goes like this. You do, and this is kind of weird, but I'll explain why this is in just a minute. You factor the delta x out because each trapezoid is going to have a delta x in it, and then you do half of the first function value. Then you just add all the rest of the function values up. Then you do half of the last function value. So the idea would be, for instance, you might have something like this. You might have like half of whatever that first function value is. That's the first value. Okay, then you just do the second function value. Okay, then you do the third, and so forth. And then when you get to the very last one, you have to do half of that. I'll show you in a minute why that is. So it's kind of like that, and then you multiply that by delta x. That's the formula. And you want to use this when you're doing your homework because it's less tedious. Otherwise, you would have to individually figure out what the area of each trapezoid is and add it up. So that formula simplifies it. And again, I'll show you how that formula is derived in just a minute. Okay, so this is the Trapezoid Rule approximation, and the key thing you want to pay attention to when I say t of n, that just means that's how many trapezoids you have. So like if I said t of 5, that would just mean that we have 5 trapezoids. Okay, so the thing you want to remember is delta x is factored out of the whole thing, and what delta x is that's the height. That's the distance between the two bases. Okay, then you do half of the first function value and half of the last function value, and all the other function values you just add them up. Okay, and you'll see clearly here in a minute why that works. Okay, all right, let's go to the next page and let's go ahead and do one of these things. I want to kind of talk through this a little bit. Now this one I just took out of the book and to show you, but I'm also going to, with this one, I'm going to show you how the formula is derived. So basically, if you were doing the trapezoid rule for this integral, that's a super easy integral to do. You can easily get the exact answer on that one, okay? But the idea with this is, so if you're doing 4 subintervals, and I'm just going to talk through this, I just took this out of the book so you don't have to write all this down, is when you're doing delta x, that's b minus a over n. So what's b and what's a in this problem? 4 and 2, right? Those are the limits of integration. So it's the upper limit minus the bottom limit. N is the number of subintervals. So that's 2/4. So that's equal to a half. Okay, like that. So what you're doing on this is you're going by a half. You're starting with the lower limit, which is 2. And then you're just counting up by a half. So you're going to 2.5 to 3, 3.5, all the way up to the upper limit of 4. Okay, that's what the meaning of delta x is. That's the distance between those values, like that. We're going up by a half. So here's how this goes then, and this is pretty simple. I am going to, in this diagram, have you write down why this formula is the way it is. So all you got to do on this trapezoid formula is you do this. You do half. You can factor that delta x out of there. So that comes there. And then what you do is you just do half of the first function value. So you would just do 2 squared, like that. Okay, then you just square all the other function values. You would do like 2.5 squared, 3 squared, 3.5 squared, and then you do half of the last one. So you always do half of the first, half of the last, and then do that like that. And then that could be done on your calculator. You get about 18.75. Okay, so the idea with that one is trapezoid formula. You follow that pretty strictly, factoring the delta x out, and I'll explain now why that 1/2 shows up in there then. Okay, all right, does that make sense? Okay, it's not, trapezoid formula is not that hard to do. You just got to remember half of the first function value, half of the last, and all the other function values are just without the half. So let me show you why that's the case. Okay, so I want you to write down kind of in this diagram. I'll show you why this works out the way it does. Okay, so first of all, in this particular thing, if we do delta x is b minus a over n. So again, what you would have is we're doing the integral from 2 to 4, and we're integrating x squared dx. So again, we would do 4 minus 2 over 4 subintervals. So that's 2 over 4, so that's equal to a half. So that's what that is. Now what I'm going to do is I'm going to do each trapezoid separately, and then I'll show you how the algebra simplifies into this certain thing. Okay, like this. Okay, so I'm going to just kind of write this down like as T1, T2, T3, T4. We're going to have 4 trapezoids that we're going to do on this. Okay? Now here's what happens on this. So what I'm going to do is let's write down what the area of the first trapezoid is. The formula for a trapezoid is 1/2 the height times the sum of the bases. Now I'm just going to write that down one time, then I'm going to do this thing kind of individually. Okay, if you look at this trapezoid right here, okay, first of all, what's the height right there? What is that? That's a half. That's what delta x is. That's a half. Now what are the bases? Wouldn't that just be a function value? Wouldn't that be a function value? Okay, so what you're going to do is it's going to go like this. I've got everything set up, so you're going to go like this. You're going to go 1/2 times, that delta x, which I'm just going to write that as delta x for now, because I want you to see something on this. Okay, then this function value right here is going to be f of x naught plus f of x1 like that. Okay, that's what the formula would be for that very first trapezoid right there. It's a half times delta x, which again is this little piece right here, and then it's times the sum of the bases. The bases are function values. So tell me if that makes sense. Is everybody solid on that? I'm just applying that formula specifically like that. Okay, now let's go to the next one. Okay, well, it's the same thing. It's going to be 1/2. The height is still delta x, right? So that's 1/2 delta x. Now, the bases are going to go like this. The first base is going to be f of x1. Okay, and then the second base is going to be f of x2 like that. So that's how that goes. Okay, you seeing what's happening? Okay, let's keep going. Okay, so the third trapezoid is going to go like this. We're going to have half, again, delta x is that height. Okay, now what functions are you going to have? You're starting to see a pattern. What are you going to have? The second one, the second function value, plus the third function value like that. Okay, and then finally you get to this fourth trapezoid, and when you do the area of the fourth trapezoid, same idea. It's 1/2 delta x. Now what are the bases? The bases are these two. So you would have f of x3 plus f of x4 like that. Okay, so that's what happens. Now what I'm going to do is I'm going to develop the trapezoid rule, because I want to give you some idea of where this comes from. Now that's kind of tedious. You could go through and do all 4 trapezoids, or you can follow the trapezoid rule formula. So here's how this goes. The area total, and in here we would just say trapezoid of 4, because we're doing 4 trapezoids. If you look at this now I want to kind of show you what happens. First of all, we're going to add all those things up, right? Isn't 1/2 delta x a common factor? Yeah, okay, it's a common factor. So what I'm going to do is I'm going to pull that out and have you write that as 1/2 delta x. Then we're going to have a big bracket, and inside of this bracket what you're going to have is you're going to have all of this stuff right here. Okay, so what I'm going to have here is I'm going to have f of x naught plus f of x1 plus f of x1 plus f of x2 plus f of x2 plus f of x3 plus f of x3 plus f of x4. And then we're going to kind of, then we're getting close to the point where we can kind of see how this trapezoid formula comes together then. Okay, like that. Okay, so see what I did is I've done this. I'm just adding all these things together. And what I'm noticing is they all have a common factor of 1/2 delta x. You see what I'm doing there? Now what's left is all this stuff right here. Okay, all that stuff there. Now, what do you notice here? See how you have 2 of the x1s, 2 of the x2s, 2 of the x3s. You only have 1 of the last and 1 of the first. Okay, so this is where this trapezoid formula now starts to come together, is like this. Okay, so what I'm going to do is I'm going to do this. I'm going to try to do some of this in my head. I'm going to leave this delta x out, and then if we multiplied, if we distributed that 1/2, you'd have 1/2 f of x naught, right? Now, what's going to happen with this? There's 2 of those, right? Isn't that 2 f of x1? So what you're going to have is you're going to have 1/2 times, because I'm distributing the half, times 2 f of x1. Okay, then I take the 1/2 through the next one, and then I have 1/2 times 2 of the f of x2s. Okay, and then I've got 1/2 times 2 of the f of x3s. And then finally I've got 1/2, but I've only got 1 of the f of x4s like that. Okay, so what happens to the 1/2 and the 2? They cross out. So see, this is your trapezoid formula. So the trapezoid formula is delta x. You got to take half of the first function value. Then you just take that function. All of these you don't take a half of because it canceled out, see. And then right there is your trapezoid formula. Okay? I just wanted to show you where it came from. Okay? Does that make sense what I did there? Okay? So, you don't need to go through, and a lot of times I see students when they're doing this formula, is they individually go through and find all of the trapezoids. Don't do that. Just follow that formula. Okay? Like that, and it makes it way, way easier. So see, when we just do a little basic algebra, then that's what you get. Okay? Okay, so let's see. Let's do a trapezoid formula on this one, and then we'll take a break before we do Simpsons Rule. So let's do this same problem that we did a few minutes ago, but we're going to do this trapezoid rule. Okay? So, first thing you want to do is you want to find what delta x is. Okay, so we got n subintervals, so we're going to use n is equal to 6. Okay, what's a and b in this problem? Okay, 0 to 1. Okay, those are the limits of integration. So when we do delta x, we're going to do b minus a over n, so that's going to be 1 minus 0 over 6. So that gives 1/6. Okay, what does that mean? The 1/6 is the height of each trapezoid. Okay, that's what that's the distance between the bases. That's what delta x is. Okay, so what we need to do in the trapezoid formula is we need to know what each of these things are. x0, x1, x2, x3, and so forth like that. So again, what we're doing with this one is the formula kind of goes like this. So let's go ahead. You don't have to write this down, but I'm just going to count off by 2 6s. Like this, then I'll have you do a diagram on this, like this. Okay, so let's see. Right in the middle, you would have 1/2. And then I'll just kind of further subdivide these. I've got 1/6 there. 2/6 is 1/3. Then 4/6 is 2/3. Then we got 5/6. And then 6 over 6 is equal to 1, like that. Okay, so that's how that goes. Now, I'm going to have you do is just do a diagram on this. So, the way this goes is we do a trapezoid. So, you put like a dot there and a dot there. And then when you do your trapezoid, well, you're just drawn like that. Okay, the next one, you go straight up. And then you connect these 2 dots, you have a trapezoid. And so forth. Okay, and see, this really is accurate. I mean, it's off a little bit because you're using a line instead of a curve, but it's pretty much right on there then. Okay, so we just do that, and so forth. Okay, so what I'm going to have is, like, we're going to find, that's T1, T2, T3, T4, T5, T6, like that. So we're going to use the trapezoid formula to approximate that area. And we'll see if we're a little closer than we were, because we did this same problem with the midpoint formula a few minutes ago. Okay, so far so good? Okay, so in the trapezoid formula, all you really got to do is you got to figure out what all of these values are, and then we're going to do the function values like this. So what we're going to have here is really what I think I meant to put on here was f of x naught. So f of x naught is just going to be the sine of pi times 0. Okay, because what I'm doing is x naught is 0 right there. So we're just doing that. So those are going to be the values that we're going to evaluate the function at. So then the next one, f of x1, is going to be sine of pi times the 6th, or that'd be sine of pi over 6. Okay, and then f of x2 is going to be the sine of 1/3 times pi, or pi over 3. Okay, then we go the next one, f of x3, that's going to be sine of let's see, where am I at? Pi over 2, 1/2 pi. Then when I do f of x4, x4 is going to be the 2/3, so that will be sine of 2 pi over 3. And f of x5, I'm going to use 5/6, so that's going to be sine of 5 pi over 6. And then finally at the last, f of x6 is going to be sine of 1 pi, or just pi, like that. Okay? Everybody solid? Okay. So, now what we're going to do is we're going to do the trapezoid formula. Okay? And the trapezoid formula goes like this. What we're going to do is we're going to do T6. Okay, so if I ask you for T6, that means there are 6 trapezoids that we're summing. Let's go ahead and write the formula down for reference. So it goes like this. First of all, what we're going to do is we're going to have the delta x all factored out. Then we just do half times the first function value. Then we go like this. Then we got to go f of x1 plus f of x2 plus f of x3 plus f of x4, f of x5, and then when we get to the last function value, you got to do the half like that. So it's a real easy formula to remember. You're just factoring out the delta x, because that's the same in each trapezoid formula, then you do that. Okay, everybody with me? Okay. All right. So let's go ahead and let's crunch this out now. Some of this stuff I did outside of class with the unit circle, so I don't want to spend a lot of time on that. So delta x was 1/6, so we're going to have a 1/6 there. Then we're going to have 1/2. We're going to do sine. I'm just going to these things right here. So I'm going to do sine of, that would be 0 pi, or that would just be sine of 0. Okay. Then I just go from here on out. I'm just going to go. The next one is going to be sine of pi over 6. That does fall on a unit circle. Then we do sine of pi over 3, which also falls on a unit circle. And then sine of pi over 2. And then I got sine of 2 pi over 3. All these things fall in the unit circle on this, which is kind of nice. Okay, then the third one, let's see, I got 2 pi over 3. Now I've got sine of 5 pi over 6. And then you got to remember to do the half of the sine of pi like that. Okay, that's it. Okay, all right, everybody okay? Okay, now the unit circle, I'm just going to have you write down what you would find anyway on the unit circle. So we're going to have 1/2, and we're just going to do, all these things could be looked up on the unit circle. So I'm just going to have you write down those things. Sine of 0 is 0. Sine of pi over 6 is 1/2. Okay, sine of pi over 3, I think, is square root of 3 over 2. Okay, sine of pi over 2 is 1. Okay, sine of 2 pi over 3 is square root of 3 over 2. Sine of 5 pi over 6 is 1/2. And then sine of pi is going to be 0 like that. So I'm just looking at the y value on the unit circle like that. Then we'll go ahead and just work it out, because I want to get an exact answer on this and then use decimals on that then. Okay? All right, everybody okay? It's kind of tedious. These problems are kind of tedious. They're not the funnest thing in the world to do. Well, you know, it kind of gives you the idea of how the approximation methods work, hopefully. So that's going to give a 1/6. Let's see what we got. Those last two things cancel out, so it looks like what we have is 1/2 and 1/2 is a whole plus 1. Those things right there make a 2. Okay, and then these two things right here would be like terms, so that would be 2 of those, so that would be plus 2 root 3 over 2. So that looks like 1/6 times 2 plus root 3. So we could actually get an exact answer, not to the integral, but to the approximation. Then I'm just going to have you, I did this on a calculator already, so that's 0.6220084679 like that. Okay? All right, so that would be the trapezoid approximation on that then. Okay? Now what I'm curious about is, I'm going to go back to the midpoint, okay, and I'll come right back here and I'll let you do this. I want to do wherever my midpoint answer was. I want to show you kind of what we had there. So I did this same problem, I think, on example 3. And what did we get? We got this. So I'm going to take a snapshot of this, and we'll compare the two. So that's the midpoint approximation there. And let's see how close we are in these two things. Okay, all right, so here's what we have. Okay, so if you look at this one, so they're off, the first decimal's the same, but when we get into the second decimal, you start losing some accuracy. So which one do you think is more accurate? Trapezoid, okay? Yeah, we got the exact answer, and when we did the exact answer on this, I forgot what the exact answer was. Was that one the one that was 2 over pi? Yeah, okay. So what I was going to show you on this then is the exact answer, if I was to do 2 over pi like we already did, oops. Okay, gives that. Okay, so 6.3, see how it's kind of in the middle? So you got the 0.62 is the trapezoid, and then the exact answer, so we're accurate within 1 decimal place just by doing a small number of trapezoids. So that's your trapezoid, that's the midpoint, and then 2 over pi, which is about 0.636, and then a bunch of decimals is the exact answer. Okay, so that's kind of the idea. Kind of tedious, isn't it? Okay, so that would be how you would do the trapezoid rule on that. So let's go ahead and go to the next page and finish up the kind of the errors, and then we'll go ahead and take a break here. Okay, so let's see. I think we already got the exact answer. I think we had the integral from 0 to 1 of sine pi x dx. We already got that earlier. We got that as 2 over pi. So that was, let's see, on the calculator, 0.6366197724, like that. Okay, so let's do the trapezoid thing. So now what we're doing is trapezoid. So if we do the absolute error, okay, we do the formula c minus x, where c is the trapezoid, okay, and I need to go back and kind of take the trapezoid answer here, okay, which was 622, and let's see, let's get that, and we'll do, that's all I need is that one little piece of information there, and we'll go ahead and do that, and we'll do the absolute error and then compare the two like that. Okay, so the absolute error would be when we did the trapezoid rule, we got this, and then we're going to subtract the 2 over pi, like that. So I can do that on the calculator now, and that'll give us the absolute error. So let's see, 0.622, then 0.0084679, and 2 over pi. Okay, and that's an absolute value, so that's going to be a positive answer. That's about 0.0146113045, like that. Okay, and then we're going to do the relative error. Okay, the relative error, remember what you do is you just do the absolute error and you divide it by the exact answer. So I'm going to do that on the calculator, just taking what I have. I've got the absolute error there, and I'm going to divide by 2 over pi, and I'll get a positive answer on that because of the absolute value. So that's about, let's see, 0.022951334. So in terms of a percentage, if you move the decimal over 2, that's about a 2.295, round to whatever you want to, about like that. About a 2.3% error is about what you get there. Okay, so that's the idea. Okay, fun stuff, isn't it? Okay, no, it isn't that fun. It's kind of tedious, but it's important to kind of get the ideas how this does. Okay, so let's go ahead and take a break in about 10 minutes. And this one is, we're going to do this integral. We're going to do 4 subintervals, so we're going to do 4 trapezoids. On a test, I'm not going to have you do 10 trapezoids. Maybe 3 or 4 at the most is good enough. Okay, so let's go ahead. We need to do delta x. So how do you do delta x? You do b minus a over n. Okay, that's telling you how to subdivide that. So what's b? B is 10. What's a? A is 2. And then n is the 4 subintervals I'm giving you. So that's going to be 8 over 4. So that's going to be equal to 2. So all that's going to mean is we're going to, did I give you guys this graph on your handout? Okay, so I just did this on a graphing calculator. So let's see, there's 2. And that must be all the way up to 10. Now this has got some pretty big y values on this. I'm pretty sure this probably, that would be all the way up to 200. You might want to label that because I'm just doing 10 to the second times 2. And then that would be 100 like that. So what we're going to do is we're going to count by 2s on this. So we're just going to go 2, 4, 6, 8, and then 10 like that. Let's go ahead and get our diagram drawn on this. So what we're going to do is the trapezoids. So you're going to take this function value, that function value, and then make your trapezoid out of that. So just go ahead and connect kind of like that. That'll be your first trapezoid, and then that's your second trapezoid. I'll just label these like that. And then all the way up like that. So that would be the way that you would want to get that one set up, is like that. Okay, so it's a pretty accurate, you can tell on a curve like this, like a quadratic, it's a very good approximation. Okay, and the more trapezoids we do, as delta x gets smaller and smaller, then it gets closer to the precise value. Okay, all right. Now what I'm going to have you guys do, we already got we got n was what was n? 4. Okay, and then we just got delta x was 2. So I'm going to go ahead and let you guys work this out and get your approximation and your errors. So I'm going to write down the formula on here too. So what you're doing is you're approximating the integral from 2 to 10 of 2x squared dx. So what you need to do is you need to go ahead and evaluate these function values like this. And the function values you can get with your calculator if you want to, but the values on the graph are this. So basically what you have is, that would be x0. x0 is 2, x1 is 4, and so forth like that. So if you want to write a note down on that, it would go like this. x0 is 2, and then you're just going by 2s. x1 is 4, x2 is 6, x3 is 8, then x4 is 10 like that. Now I'll go ahead and write the trapezoid formula for you. You're going to be doing t of 4. So the trapezoid formula, the general trapezoid formula, I'm going to write for you here, just at the side, and you can just refer to it. You don't have to write it down if you don't want to. So it would be, when you're doing t of 4, you're going to do delta x, then you do 1/2 of the first function value, and then you do just the second function value, then the second, and then the third, and then what do you do with the last function value? Take 1/2 of it, okay? So I'm going to let you guys kind of take it from there. What you want to do is go ahead and do these. You can do this with your calculator if you want to. You're just going to do plug into 2x squared. You're just going to do like, these are your x values right here. Just crunch those out, and then use your trapezoid formula and see if you get that okay. All right. So I'll give everybody about 5 minutes to do that. Then when you go to the next page, what I want you to do is go to the next page and go ahead. I'm sorry, at the bottom of the page, I want you to do the exact integral and then find the absolute and relative error. Okay, so I'll give you about 5 minutes to work through that, and then we'll see if we're on the right track with this. Okay, I'm just going to pause this for and run through. If you're still working on doing the error and stuff, you can do that. But if you didn't get the 672, you want to look up here and make sure you did that right. So you're going from 2 to 10 by 2's. And again, we're looking at the function 2x squared. So if you did these function values, you should have got 8, 32, 72, 128, and 200. Right, that's the first thing that you want to make sure that you did, because I'm just doing 2x squared, and then you could use your calculator on that. Now your trapezoid formula, again, goes like that. You have the delta x, which is, we figured out that delta x was 2. We already had that, so that's factored out of there like that. Then you're doing half of the first, and then half of the last like that. So it's arithmetic. If you made an arithmetic error, just identify what that error is. But you want to make sure that you understand how to use that trapezoid formula. Very easy to remember. Just remember to do half of the first function value, half of the last, and then add up the rest like that. Okay, has anybody got a question about that? Okay, we solid with that? Okay. Now, let's see. The next thing here, what did you get for the integral, the exact answer? Anybody get that? 1984 over 3, right? That's what you should have got when you did the integral, and that's a real basic integral. So I'm going to go to the next page right here, and you can copy it down, or just if you didn't get this. So that's a super easy integral. The antiderivative is 2x to the third over 3, evaluated from 10 to 2. So I just ended up doing 10 to the third minus 2 to the third, factoring out the 2/3. And then if I multiplied that out, I got 1984 over 3. Now you could change that to a decimal, but that's good enough. Okay, when you get an answer like that, you don't need a decimal with that. Okay, now as far as the errors go, it would go like this then. If you did this correctly, 672 is what you would have got on the trapezoid rule. And then if you compare that to the exact, you can do this on the calculator. You can get a decimal on that too if you want to. But if you want to do, remember you can do fractions pretty quickly on your calculator. If you do 672 and then minus the 1984 over 3, don't forget your calculator will do fractions for you. So you can get that. And then if you want to go math fraction, it'll convert that anyway. So that's what I did, is I just changed that to 32/3 to save a little bit of time. Let my calculator do that. Then I do the relative error. And if I do that, relative error means that you're taking the absolute error and dividing it by the exact answer, like that. And I just used a percent on that, so I got about a 1.6% error. Okay? There's not that much to it. You just have to be very careful about all the arithmetic when you do that then. So that's kind of a type of thing that I test people over with a calculator. Okay, how's that look to everybody? That's not bad. Okay, and the trapezoid rule is not that hard to remember. If you just remember the half on the first and last terms, and it's a lot of tedious calculations, so that's not too bad. Okay, that's a reasonable test question right there. What do you think? Okay, with calculator. I wouldn't expect you to do that without a calculator. Okay, any questions about anything? Okay, so let's finish up with Simpsons Rule. So I wanted to do just kind of talk through that. I think there was one page of your notes that didn't post right too, so I'm just going to have you write. I'm going to do one Simpsons Rule problem. So Simpsons Rule, what I'm going to go through on that is you got this weird formula, and Simpsons Rule uses parabolas. I'm not going to go through a lot of derivation on this and everything, but the idea is you might want to just maybe write down a picture here. So let's say, for instance, that you're integrating from some interval a to b like that. Let's say that's a to b, and let's say that you have some curve kind of like this, and let's call that's f of x, okay? Now what Simpsons Rule is doing is it's using a parabola to estimate. Okay, so typically what happens on this is, you can subdivide it into different units like that, but typically what you're doing is if we just did some subdivisions like that, so from there to there, we would have this like a little piece of a parabola. This is not a real good diagram on this, But like for instance, if you were going from there to there, you could have a little piece of a parabola right there then. So without going through a lot of the details, I'm just going to show you how to use the formula on that and kind of talk through the formula. Then we're going to do one example in class. Then I'll talk about this table thing here. So I want to do mainly one example on here. So basically, you have to have n is an even integer. N is how many things that you're subdividing this up into. Delta x still means the same thing, b minus a over n. And the formula is kind of weird on this, and let me talk through what this one does. It's kind of crazy, but it kind of goes like this. You have delta x over 3. I'm not going to derive that or anything, but that really comes from the fact that if you're doing a parabola, you find 3 points on there, and then you do find an equation of a parabola. Then it goes like this. You take the first function value, then you take 4 times the second, 2 times that, and then it alternates forever. It goes one of those, 4, 2, 4, 2, 4, 2, 4, 2, then you get to the end and you just have it. So it's kind of like trapezoid. You have half of the first, half of the last. Well, in Simpsons Rule, it's kind of weird. It goes 4, 2, 4, 2, and alternates forever like that. Okay, till you get up to the end like that. Now, what I want you to do, I think, before I go through this thing here, I wanted to just kind of do one main example. And I think this problem didn't come out on your handout. It was supposed to be a page 10. So what you can do is you can go to the back page if you want to and just write that down. So my intention was to do one Simpsons Rule problem, okay? Just one. So if you want to write this on the back, that's fine. And then if we have time, I'll go back and show you what the relationship between Simpsons Rule and the Trapezoid Formula is. So we're going to do this one. So I picked out something like this. This one actually integrates. It's 0 to 3, 1 over 1 plus x squared. So we're going to do 6 subintervals, and we're going to do Simpsons Rule. Okay. So I want you to be able to crunch out Simpsons Rule. It's kind of tedious. It can be kind of tedious. Okay, so I went ahead and did this. You don't necessarily have to write that formula down unless you want to. I just took that from the previous page. You already got that on there. So first thing we're going to do is find delta x, which is b minus a over n. Okay, so b is 3, a is 0, and then n, this time we're going to do 6 subintervals. I like doing a half, so that works out to be a half like that. So what we're going to do is on this one, I'm going to take my calculator. I don't even know if I really need to do my calculator on this one. I'm just going to crunch out the details with this one. So what we're going to be doing is we're going from 0 to 3. So if we count this out, we're going like 0, a half, 1, 1 and a half, 2, 2 and a half, and then all the way up to 3. Now you can use decimals if you want to. You can use 0.5 and 1.5 and so forth like that. So this is going to be x0, x1, x2, x3, x4, x5, x6 like that. Okay, so we got everything kind of counted out. Now what we're going to do is we're going to evaluate the function, and then we're just going to crunch out Simpsons Rule like this. So this one, if we're doing f naught, what you're going to do is you're just going to go to the function, which is 1 over 1 plus x squared, and we're just going to plug in these values like this and crunch these out. So we're going to do that. First of all, it's kind of like Trapezoid Rule. You kind of start off the same way. So that's 1 over 1. So that's going to be 1, like that. Okay, then I go to F2. So what I'm going to do on this is I've got 1 over 1 plus 1/2 squared. Okay, I'm going to do this without a calculator as much as I can too. So that's 1 over 1 plus 1/4 if you square that. Okay, now the best way to do this is just kind of review the fraction, a complex fraction. If you multiply the top and bottom by 4, that'll get rid of that. I'm going to go ahead and get a fraction answer on this and do decimals at the very end. So what I would get is I would get 4 over 4 plus 1. So that's 4/5. Now tell me if you follow that okay, because that's complex fractions, and sometimes students forget how to do that. I have 1 over 1 plus a fourth. I'm just trying to get rid of that 4. So I have 4 in the numerator and 4 plus 1 in the denominator. Okay, that's getting rid of the fractions. Okay, now go to, so we've got that done, we got that done, now we go to x2. So that's going to be 1 over 1 plus 1 to the second. Okay, so that's going to be 1 over 2, so that's going to be 1/2, like that. Okay, so we're done with that. Now we go to 3/2. So we're going to go 1 over 1 plus 3/2 to the second. So that's going to be 1 over 1 plus 9 over 4. Okay, so again, I'm just counting off by the half. Okay, and then this one, I'm going to multiply the top and the bottom by 4. Okay, when I do that, I would have 4 over 4 plus 9. So that looks like that's 4 over 13. You guys see how I'm doing that complex fraction okay? Okay, now make sure you know how to handle that kind of thing like that. And then we can, I'm going to use the calculator kind of at the end on here to help me a little bit. So then we're ready now to go to 2. So we're going to go 1 over 1 plus 2 to the second. So that looks like that's 1 over 5, like that. And then we're ready to go to 5/2. So that's 1 over 1 plus 5/2 to the second. So that's 1 over 1 plus 25/4. So I'm going to multiply that again by 4 over 4 to get rid of the fraction. Okay, so that's going to give 4 over 4 plus 25. So we've got 4 in the numerator. 4 times 1 is 4. 4 is crossed out, leaving 25. So that's 4 over 29, like that. Okay, and then the last one would be the 3, so that's pretty simple. We go 1 over 1 plus 3 to the second. So that's 1 over 1 plus 9, or 1/10, like that. So what I was doing was, if you kind of notice what I'm highlighting right here, is I'm just evaluating the function from 0 to 3, but doing subintervals up a half, like that. Okay, everybody with me on that okay? Okay. That's a ton of arithmetic. It's not that hard. It's just kind of a pain to have to do all this arithmetic. So what I'm going to do now is we're going to do Simpsons Rule. We usually represent that S of n. So we are doing 6 subintervals in the problem. That's part of the problem. So here's how this basically goes, is like this. What you do, first thing I want you to write out is the formula. I like to put the delta x over 3 in front. The book kind of puts at the end. So here's what you do. And you want to write this down. So this is how I remember this. It's not that hard to remember. You do f of x naught. Then you go to 4, f of x1. Then you go to 2, f of x2. Then you go back to 4, f of x3. Okay, then you go back to 2, f of x4, then back to 4, f of x5, and then when you get to f of x6, you just leave that the way it is. Like that's a weird formula, that's the way it goes. So what you do is the first and last term are just the function, and then all the rest of the stuff alternates. Starting with 4, it goes 4, 2, 4, 2, 4, 2, like that. Okay, that's kind of weird, that's the way Simpsons Rule goes. So what I'm going to do on this is we're going to go ahead and just get the answer of this, and I'm going to use my calculator on most of this. So let's see, delta x was 1/2. Now I'm just going to put these values in. So I've got f of x naught is 1. Then I've got 4 times, let's see, 4/5. Okay, then I've got 2 times 1/2. And then 4 times 4/13. And then 2 times 1/5. And then 4 times 4, what is that, 4 over 29. And then plus 1/10, like that. Now see, all I'm doing is I'm just taking the values that we crunched out. The 1, 4/5, 1/2, 4/13, and so forth, like that. Okay, yes?
You only have to divide delta x by 3.
You have to what?
Divide delta x by 3.
Yeah, well, you got to, oh, it's by 3. I forgot on that. Thank you. I didn't do that right. So you got to have delta x was a half, so you got to divide that by 3. Okay, and if you do a half divided by 3, what's that going to be? 1/6. Okay, so I'm just going to erase that and make that that thing right there becomes 1/6, like that. Okay, well, then you just put this on your calculator. I wouldn't expect you to do this any other way than just do it this way. Okay, so actually what I'm going to do on this is this real quick, just kind of finish this up. So I'm going to do what's inside the parentheses. I'm just going to try to do that in one step. So I'm going to go 1 plus, whatever I can do in my head, I'm going to do in my head. That's 16 over 5, like that. And then these would cancel out, leaving a 1. Okay, then I've got 16 over 13, like that. Then I've got, what, 2/5. I'm just multiplying in my head. Okay, then I've got 16 over 29, like that. And then the last thing I have is 1/10, like that. Okay, so hopefully I got everything in there right. Now what I'm going to get is a decimal, but I'm going to convert it back to a fraction. So if you're doing your homework, just let your calculator do all this stuff. Don't spend all your time on these fractions. Do that, then go math fraction, and you'll get that crazy answer like that. So it looks like we have 1/6 times, now that says 28,209 over 3,770. Okay, now what I'm going to do is just do the 6 times the 3770, like that. So that gives about 28,209 over 22,620, like that. Isn't that great that we have technology that can do all this stuff for us in this day and age? Okay, I'd hate to have to do this without technology. So if I just do a decimal on that and take 28,209, and that fraction may reduce, I don't know, 22,620, and I'll just write down the approximate decimals, about 1.247082228, like that. So that's how Simpsons Rule works. It's not that hard. It's pretty similar to the trapezoid formula, except you got the delta x over 3, then you got the alternation of the 4, 2, 4, 2, like that, and so forth. Okay, you guys follow that okay? Okay? All right, well, I'll wrap us up for today. This stuff to me is not the funnest stuff, but it's necessary when you have an integral that you cannot integrate. Then you have to do it numerically. That's the point.